Hello everyone, we are Group 7. I'm the leader of this Group 7. So I would like to present the title related to the video presentations about the linear programming approach, including the solutions of case problem. So let's take a look about the introductions or concept of linear programming. So linear programming is a mathematical method which they are able to make an optimizations which can have minimization costs or maximize the profit. They are subject to constraints which the constraint must be linear or including the inequalities or the equations. It's about finding the best solutions under limited resources. So for here, there are 5 key components of the linear programming, which were decision variables, objective functions, constraints, feasible region, and also optimal solutions. The decision variables is the unknown values that you want to determine, while for objective function is a linear equation that you want to maximize or minimize some objectives, while the constraint is the limitations of equation such as budget, time, manpower, materials, and so on. This linear constraint is under inequalities or equations. The example was given on the slide given. While for flexible region, this one is under the area on a graph where all constraints are satisfied. So the optimal solutions must be lied within this region. Therefore, for the last part about the optimal solutions, the optimal solution is the point in the feasible region that gives the highest profit or the lowest cost. Now, let's take a look about the benefit of using the linear programming approach. So there got 6 types of benefits when we using the linear programming to solve the problem. So for first, when you use the linear programming, it can optimize the resources, maximize profit and minimize costs, enhancing the decision making, reduces waste, solve the true decision variables problem that are easily compared to simplest method, and also the last benefit is widely applicable. When we are able to optimize the resources, the manager can allocate the limited resources such as time, money, labor, materials in the most effective or efficient way. While for the part of maximize profit or minimize the cost, the manager can find the best combination of decisions to achieve the objectives like higher profit or lower cost. Besides that, let's talk about the benefit about enhancing the decision making. The manager can provide a systematic or scientific approach for planning and choosing the best course of actions. Furthermore, for the fourth benefit, there was reduced waste. Manager can ensure the materials, labor, time are not underutilized or overutilized. Same goes with the other benefits. It can solve the 2 decision variables of the problem easily by using graphical method to find the optimal solutions without using the simplest method. Lastly, it can be widely applicable. This linear programming can be used in production planning, transportation, scheduling, inventory management, agriculture, and also the finance. So I would like to talk about the introduction of the case studies. So let's take a look about this case study. For the information given, the Angela and Zoe need to prepare 2 types of dinners, which were fish and also the beef. So the questions given, each night have maximum to sell 60 meals, while the labor available that only got 20 hours each day. When prepare a fish dinner, it requires 15 minutes, and also for the beef dinner need to take twice as long, which means for preparing a beef dinner need 30 minutes to prepare it. While it also got a ratio equation that is they will sell at least 3 fish dinners for every 2 beef dinners. And lastly, the constraint is related to they believe that at least 10% of the customer will order the beef dinner each night. So this is the constraint given. So I already explained about the constraints. So for the objective functions, it's about the maximization profit, which each fish dinner will get a profit as $12, while the profit for a beef dinner is about $16. So for the further questions for the theory, I will explain it later. Therefore, for this part, I already mentioned about the constraint and also the objective functions. So let's take a look about the part of solutions for further informations to solve these situations or this case study by using the graphical method.
Let's define the variable for our problem. Let x1 be the number of fish dinner, so it's 9. Let x2 be the number of beer dinners, so it's 9. Our goal is to find value for x1 and x2 that satisfy all of the following constraints. Constraint A. First, there is a limit on the total number of meals we can sell. We can sell a maximum of 60 meals is 9. This means the number of fish dinner plus the number of beef dinners must be less than or equal to 60. Mathematically, this is written as x1 plus x2 is less than or equal to 60. Constraint B. Second, we are limited by our available staff labor. We know that a fish dinner requires 15 minutes to prepare, which is 0.25 hours. A beef dinner takes twice as long, which is 30 minutes or 0.5 hours. We have only 20 hours of labor available each day, so the total preparation time for all meals cannot exceed 20 hours. The equation for D is 0.25 times x1 plus 0.5 times x2 is less than or equal to 20. We can simplify this by multiplying the entire equation by 4. This given us as equilibrium contrast x1 plus 2 times x2 is less than or equal to 80. Constraint C. Third, this is a specific sales ratio we must maintain. We need to sell at least 3 fish dinner for every 2 beef dinner. In radio terms, this means the ratio of x1 to x2 must be at least 3 to 1, 3 to 2. This is written as x1 over x2 is greater than or equal to 3 over 2. We can rearrange this by cross multiplying to get a 2 times x1 is greater than or equal to 3 times x2. Contrast D. 4. This is a minimum demand for beef dinners. At least 10% for all customers must order beef. This means the number of beef dinner must be greater than or equal to 10% of the total meal sold. The inequality is x2 is greater than or equal to 0.1 times the quantity x1 plus x2. If we solve this, we subtract 0.1 x2 from both sides to get 0.9. x2 is greater than or equal to 0.1 x1. Finally, dividing both sides by 0.9 given us x2 is greater than or equal to 1 need of x1, with the decision variable with x1 and x2 must at least 0, which is non-negative for all constraints.
After determining the constraint based on case problem, we will go through the graphical solution for our dinner sales about case problem as maximizing the profit by how many fish and beef dinner we should sell by fulfilling all the constraints. For first, we need to use the constraint into linear equation to determine the x-intercept or y-intercept. Even our linear graph look likes, on the first slide, you will see our calculations. We will take our constraint equation like x1 plus x2 equal to 60 and found the intercepts by setting values to 0. This tells us exactly where our line crosses the axis. We'll also calculate the points for our ratio constraints, where x2 is 2/3 of x1 and where x2 is 1/9 of x1. By plugging in sample numbers, like 30 or 18s, we get the precise coordinates needed to draw the slope of these lines. After getting the coordinates of each linear constraints of graph, we may plot the graph. The most important part of this chart is the shaded triangular area in the middle. This is our feasible region. It represents a valid combination of dinners we can sell that follow all our rules. In linear programming, the best answer is always found at one of the corner points of this region. Looking closely at the intersections, we have identified 3 critical corners. The first at coordinate 34 and 23, the second at 40, 20, and the third at 54, 6. Finally, let's determine the optimal solution of maximizing profit from these corners. Our profit formula is x equal 12x1 plus 16x2. This means we make $12 profit on fish dinners and $16 profits on beef dinners. We simply test our 3 corners by plugging them into this formula. The first point, 34.23, our total is $776. At the third point, 54.6, the total is $744. But, looking at the middle calculation, when we sell 40 fish dinners and 20 beef dinners, our math gives us $480 plus $320 for a total of $800. Therefore, based on this graphical analysis, the optimal solution to maximize our profits to $800 is to sell exactly 40 fish dinners and 20 beef dinners. Thank you.
What is the effect if price fish increase so profit for both dinners was same? First, for maximization, selling the meals of constraints, we can know that the maximum profit is $960. Second, by checking the values of 3 coordinates, which is 34.23, 40.20, and 54.6 into these constraints inequalities, we will get another 2 new constraints, which is for 3 and 4. Third, substituting 3 into time constraints, which is x1 plus 2x2 not more than 80, to determine maximum value of units sold to get maximum profit and fulfill all constraints. And lastly, substituting 3 into x2 more than 1 over 9x to find minimum value of beef dinner must be sold to fulfill constraints and maximizing profit. In conclusion, this question had multiple feasible points, which means had many optimal with mid solutions. When price of fish dinner increase and same with price of beef dinner, this linear programming approach do not have unique solutions, which means the inequalities of beef dinner must be between 6 to 20 and fish dinner must be between 40 to 54, which satisfied for x1 plus x2 equal to 60 to get maximum profit respectively since the other constraints unchanged.
For this part, what happens to the maximum profit if we increase the required minimum demand for beef dinners x2 from 10% to 20%? Now we talk about the change. The original constraint was easy to satisfy, but the new constraint required x2 to be at least 20% of the total dinners, which made the feasible area on the graph slightly smaller. So the new constraint will be x2 greater or equal to 1 over 4 x1. By using the new graph solution, the coordinate for new constraint was 25 and 40, 10, while the others was unchanged. After that, we can find the new corner points on the graph which were 34, 23, 43, 20, and the last one is 48, 12. When we test this point in the profit function, the result will be $776, $800, and the last one is $760. In conclusion, the change had not effect on the optimal solution. The maximum profit remains $800.
and the optimal production plans remains 40 units of X1 and 20 units of X2. This happened because the original plan was already safe enough that it still certified for the new changing.
Lastly, in summary, linear programming is a mathematical method to find optimal solutions within two variables easily. For the solutions part, from linear programming approach for finding optimal solutions for this case study, for the fish dinner which is under decision variable S1 and 20 beef dinner which is under decision variables S2 is getting maximum profit by using maximum labor hours with fulfilling all the constraints. Besides, if the price fish dinner increase and same as the price beef dinner, it will exist many optimal solutions. It means that any flexible solutions that pair with 60 dinners with any conditions that at least 6 until at most 20 beef dinner that need to be sold. At the same time, fish dinner must be sold at least 40 until 54 plates or unit to fulfill the constraint to get the maximized profit. Lastly, if consideration of beef demand raised from 10% to 20%, no effect for changing plan or preparing meals. It still remains 40 fish dinners and 20 beef dinners to get a maximization of the profit. Thank you so much. That's all for today. Thank you for listening the presentations. Share a Canva slide related to this case solutions. You guys need to copy and paste and then write your own point. This is your task I given for you. Okay, can understand what I mean or not? Others, you just can react. You don't want to talk, you can react. Okay, okay. I think that's all. Okay.